of a supercrystal with nanoscale periodicity. Venkat, if you'd like to start, go ahead.
Hello. So can you see my screen and hear me?
Yeah, I can see your screen great and hear you great. So
awesome. Okay, yeah, thank you for the invitation. I really appreciate it. It's a wonderful session and a lot of great talks here. So we're going to continue this PTO, STO lead titanate, strontium titanate superlattices that Ramesh and Lane Martin's group at Berkeley have been synthesizing and doing a lot of wonderful work on. And Vladimir Stoica is our postdoc who primarily did the work I'm going to talk about today. A theorist, Long-Ting Chen at Penn State, and APS folks, John Freeland, Hayden Wen, have contributed greatly here. All right, so I wanted to point to different types of wall that other speakers have mentioned: Ising, block, nail. You can have mixed walls as well. And typically ferroelectrics tend to be this, where the wall literally, if you want to flip a polarization, it has to go to zero and flip over instead of rotating it in a plane, in the plane of the wall, or tumbling over across the wall. These are things that spins can do very well because they're not so strongly coupled to lattice, but polarization has a hard time doing. And so one of the questions is, can we create non-Ising polar structures? And the answer is yes. And you have seen that in the last 3-4 talks. All types of um, vortices, fermions, supercrystals, and so on can be formed. And the idea is to frustrate the system. So this paper here had an idea about barium titanate and strontium titanate. And for many years, we were looking for this, but it's much harder to find these things in barium titanate. And Ramesh's group um, published this in 2016 with lead titanate, strontium titanate, and beautifully you do indeed see these vortices. And the basic idea, again, is of frustrating the system so that the polarization can do these so-called dances. So the lead titanate is under compression, it's shown by this arrow, strontium titanate under tension. So you're sort of going compression, tension, compression, tension. So lead titanate really wants to stand up because it's under compression. The other thing is, of course, this is ferroelectric and not ferroelectric and so on and so forth. So there are two types of frustrations that are interwoven. And so the polarization wants to stand up, but it runs into this wall. That's going to give you, by Gauss's law, a huge charge buildup. So it tries to avoid, so it goes left or right. And then it goes down the other way, it has to turn around again. So it automatically starts swirling around. These yellow arrows are pointing to the lead displacements pulled out from a transmission electron microscope. Okay, so more work from Ramesh's group where you can play with the period. You can get step ladder type domains or closed domain structures where you can have well-defined domain walls and so on. But somewhere in the intermediate range, these things, the walls kind of become diffuse and you get what are called vortices. And this is an example of Long-Ting Chen's group doing a simulation. And one of the nice things about these systems is the physics is rather simple in some way, and the complexity is the feature, meaning you have to put in the Landau energy, the strain energy, the electrorestriction, and gradient, which is interfaces and domain walls, and that's it. So in some sense, it's simple, and so you can focus really on the complexity if you play with the periods and duty cycles and materials and so on. So it turns out the sample we'll be talking about today have these vortices, right and left-handed, and these are I call them spring rolls. And then you have these step ladder type domains, A1, A2. These are conventional domains. There's a mishmash of these two, the vortex phase and this A1, A2 phase. This is our starting material for everything I'm going to say from here on. And you can see in the X-ray diffraction, this is reciprocal KL space. And here is the substrate, this vertical line. And the ferroelectric phase has slightly smaller K values, and so slightly larger D spacing, and the vortex is on the other side. So they are mismatched on either side. Now what will happen is I'll show you a supercrystal will form. These two phases will merge into one single phase called the supercrystal phase, and it'll be beautifully in phase, lattice matched to the substrate. It finds this lattice matching. Okay, so the basic experiment that Vlad Stoica, our postdoc, very creative idea he had was to take these mishmash and hit it with an optical pulse. It's just near the edge. There is already absorption picking up. It's not above the edge, but already you're generating a whole bunch of carriers and dumping them in there. And the idea was if you flood these interfaces, we know interface charge plays an important role. What happens if you flood it? And while he is doing that with a 400 nanometer pulse and very short pulses, he's looking with hard X-ray nanoprobe and looking at the reciprocal space at these super lattices. These were all 16 by 16 unit cell super lattices. So all of the work was focused on one set. With X-ray imaging microscopy, so if you take the D103 peak and find the strain, so there's the relative strain in 103 reflection, you can make an image, you can see the two mishmash phases, this vortex phase in A1, A2. The blue is the vortex and the A1, A2 is the red. And you can see there's a big spread in strains. And the amazing thing that happens is once you hit it, even with a single pulse with enough fluence, this entire mishmash turns into one single phase whose strain is pretty much near the center. Okay. Pretty much, the strain contrast has been erased. And from diffraction, this is a single giant phase. And I'll show you, we call this a supercrystal. So this is reciprocal space, and you're seeing, I'm going to talk more about these diagrams, but this is mixed phase before, and it turns into this beautiful diffraction pattern with all of these extended higher order peaks. And we really do this in the reciprocal space in 3 dimensions. We map it out. And it is very important to do that because as you'll see, these unit cells are huge and there's a lot of complexity. Whoops, my talk just gave up.
Go ahead and just try to restart that.
I'll do that.
See if it comes back up.
Yeah. Sorry about that. Well, I upgraded my operating system to Mac Sur, Big Sur or whatever, and that's a mistake, so don't do that. So the system has slowed down considerably. All right, let me swap displays. Okay, I think I skipped that video and we should be okay now. You're good? You can see this?
Good. Yeah.
Okay, great, thank you. And so let's just take some cross sections. And here is the pristine phase. You can see these splittings. One of them is the A1, A2 phase. The other one is the vortex. And these are ordered. So there's the 0th order of the both. And then the first order, there's the -1 order and so on and so forth. Okay. And this periodicity here is really defined by the 16 by 16 unit cells. And this was after, so right, before and after. And now you can see a lot more structure. Let me walk you through this. So this spacing here is 12.5 nanometers, and this is the period of growth. So it's really defined by growth, right, in Ramesh's lab. And with the new phase that we create optically, there's this extra reflection, and now this corresponds in real space to double this period, so 25.1 nanometer. So in some sense, every other lead titanate layer is now different. So it's like doubled in this in the z direction. If you look in plane, you now have this um, you have the period of 29.5 nanometers. So if here is in this corner, you can see, let me see if I can get my laser pointer back. So in this corner, you can see these are the vortices. The K is along the vortex and L is vertical. So you're looking at L and K. So this is along the vortex. And so along the vortex, now there is a 30 nanometer period. Okay. If you look at H and L, now H is perpendicular to these vortices. You see something very similar again with the two mixed phases. This is after. That is 11 nanometers, and that is here, the 11 nanometer on this corner is shown. That's the period between the vortices. And after, and this is the same as before. There is a doubling in the z direction, as we already talked about. And in the other direction, you have another 30 nanometer in addition to, there are two periods really that show up. The 11 nanometer is still there, but there is an additional 27.5 nanometer period that shows up in perpendicular to these vortices. All right, so this is the third cut, which is the H and K. It's very interesting because you see all these periods I just mentioned, 29.5 here. In this direction, it is 11 and 27.5. This is the direction perpendicular to the vortices. This is parallel. And you can see there's even an interplay between the newly developed periods because this and this period interact to give you this one and so on. And if you can use some of these peaks and do X-ray imaging, you see there is a majority phase, we call it 3D supercrystal. And there's also a minority phase, which we call 4D. And the fourth dimension really is one particular dimension where you have two periods. Okay? So I'm going to focus really on this 3D period for the rest of this talk. If you look at one of the lead titanate layers, and this is a phase field modeling, I'll say more about how we got this. This is Long King Chen's group. So there are vortices, as you can see, and vortex, anti-vortex pair, or clock and counterclockwise vortices. But now there are vortices in the other direction. There is a clock and counterclockwise. So it's really like a three-dimensional network of vortices, one horizontal and one vertical. And these vertical ones can even thread through multiple lead titanate layers and be coherent. So it's quite a complex structure, almost like reminds me of DNA origami. So now, just to summarize all of this, this is phase field modeling simulation that I'll talk more about in the next few slides. You've got 4 different periods, 2 of them in the same direction. So it's really then a 4D, but if you just focus on the majority phase, we call it the 3D phase, you can see order of 30 nanometer period. It's a huge, huge unit cell. And we got this image on the cover page. So they chopped it right there. So let me say something about how we initially did the phase field modeling, and now we're doing something different. In order to simulate what light does, we figured, well, it induces carriers, and the carriers are going to increase dielectric constant. And we had something called the background dielectric constant, which is sort of the dielectric constant when you heat well above the transition temperatures. If you take out the contributions due to the polarization itself, we really arbitrarily at this stage decided to use that as a knob and vary that, and went from a few, a 2 or 5 or something is usually assumed, and we decided to go up to 100. And what you can see is this is some sort of order parameter out of plane polarization that tells you whether supercrystal is forming. You can see that beyond a certain threshold value, it switches to the supercrystal phase. Okay? So somehow we have captured a lot of complex physics with a single parameter here, and we've got this what looks like the supercritical phase we are seeing. If you look at the total energy, you can see that Landau and elastic energy sort of go down, and the electrical and gradient energy go up. The gradient energy, obviously, because these polarizations are weaving in and out and making very complex patterns, so the gradient terms are going up. And overall, if you add the blue and the red, there is a hump, so that's sort of like an activation barrier, and then it gives a bigger local minimum, a bigger minimum, a lower energy state, where we call this the metastable state. This is a supercritical state. Um, and the interesting thing is this is metastable. It stays around, it sticks around for a long time, as long as you want, until you heat it to 450 Kelvin. But if not, it'll stay here. But it is not an equilibrium state. If you erase it, you have to get it back only through this non-equilibrium means by hitting it with an ultra short pulse light. You cannot just do equilibrium things and get this phase. So we had, here's some verification, phase field modeling. You take the FFT, you can see some of these circles similar to the experiments. Here is another cut, HK cut, and you can see some of these, the DFT, the FFT of the phase field matches those of experiments. There are peaks like these black ones that the phase field at this level has not captured. So it's not as though we have got the full picture here. When you look at some more microscopic, some interesting things happen. It looks like charges there's a charge ordered state. So there are polarizations locally that are up and down and left and right. And there are bound charges that are charge ordering. And if you actually calculate how much of this charge is there, it is approximately the amount of charge being pumped by the light. So there's a nice sort of intuition there that we're dumping charges, and this material finds this state in order to tuck it away and become an insulator again. Okay, and here is a strain. Here is strain ordering. So there's charge and strain ordering in this supercritical state. And as I alluded to before, if you heat it about around 450 Kelvin, the supercritical phase is erased. There is a phase transition, and these blue dots are those tucked away charges I was just showing you in the phase field model, and it disappears again. So those charges are released and the phase is gone. Now, if you cool it back, you don't get the supercritical back. And that tells you really that it is not an equilibrium phase, it is a metastable phase. And that really raises the question of why is this forming? And this is something that we are currently investigating. We have done some experiments, single shot experiment with much better time resolution at SAKLA in Japan. We're just analyzing data. And we also have some beam time coming up in a couple of months at LCLS at Stanford. And the idea is, we were looking with each single pulse, what is happening on the fastest timescales. Here in Japan, we went down to 1 picosecond. And there's a lot going on, but I'm showing only 2 slides. Within 1 picosecond, the vortex, remember, it's a mishmash state here. And as soon as one of these optical pulses arrives, the vortex collapses. Within 1 picosecond, it's almost gone. There's about 20% of the diffraction intensity left. And at this point, it is something. It is not the original vortex. It is what it is something we're trying to figure out. And from here up, within 1 picosecond up to maybe 20, 30 nanosecond, nothing is going on, not much. The thing is cooling. I call it the primordial soup. It is some kind of soup, and it is hot, and it is slowly cooling down. Nucleation and growth is happening. After about 20 nanoseconds, you can see supercrystals starting to form. It forms over hundreds of nanoseconds and completes the journey. So we are trying to track these very early stages of this primordial soup. We're trying to figure out what this phase is and why does it have the components. for the supercrystal to eventually form. And so this is a forthcoming story, if you will. Let me just conclude by acknowledging other efforts at supercrystals. This turns out to be quite rare, but maybe not anymore, right? So before this, if you talk about metastable states, states that are not accessible in equilibrium, I knew of only two different examples, one on tantalum sulfide, another by my colleague Rick Everett at UCSD on manganites, where he could switch between metal and insulator phases with optical pulses. And very recently, as you would have read, a beautiful paper by Zubko's group, where they have taken very similar structures, but now instead of strontium titanate, they have strontium ruthenate, so metallic layers, and they've formed these domain closure type supercrystals. A lot of very beautiful images, and these are not metastable, these are stable domains, and their superlattice is different, and so on and so forth. So I'd encourage you to look at this. And I'll just close with this. Here is another thing that Vlad flashed at me, and we haven't gone back to it yet. Here is another supercrystal that he created with a different period and different conditions. It looks like a rock salt unit cell. And we don't know what it is, and there's another story there for another day. So what my point is that I think we're going to see a lot more of these supercrystals stories, and the idea there, central idea, is that of frustration, engineered frustration, with which you can perturb, cleverly with charge and light-induced charge, or by other means, or strain, and so on and so forth. So I will stop there, and I'm happy to take questions. Thank you.
Thanks, Venkat. It's very interesting stuff. Until we have some more questions come in, I actually have a couple of questions related to what you alluded to here at the end. I'm curious if, because this is sort of some way of the system accommodating strain and charge, if by using pulses of light, by either changing the frequency or using different angle of incidence, you expect that you can create a sort of tailored length scales to manage the charge and strain in some supercrystal.
Yeah, that's an excellent question. So there's a lot of systematic studies. I think this thing could go on forever. But we did do, alluding to the question about the color of light, for example, we did check that we cannot create the supercrystal if we went well below the gap. So it clearly shows that it is important. The carrier dynamics is definitely very, very important in being able to create this phase. The other point I would like to make that we have explored is the non-equilibrium part. It turns out that the pulses have to be short. If they get to 1 to 10 picoseconds or beyond, then we can't create this supercrystal anymore. And so you have to deliver that charge, but you have to deliver it in a short period of time very quickly. You have to shock the system. And as you can see towards the end, I was showing how the system responds within a picosecond. It has collapsed, but it might be even faster than that. We don't know what else is happening on this ultra fast time scale, like femtosecond time scale. So it seems like time is another important variable in this, in trying to find new ground state or new metastable states.
So related to the color part that you talked about there and the time scale part, you said that if you go far below the gap, you don't see this type of change. Is that true even if you tune to some other resonance in the crystal at lower frequency, like a phonon or something like that?
Oh, that's a really good question. In fact, we have been doing that. We've been hitting these with terahertz and making them dance. In fact, there's a paper in print that's going to come out on the dances of vortices. And those are basically like phonons. We haven't driven them hard enough to get into the nonlinear regime where some phase transitions might happen. That would be very interesting, but somewhat challenging. We need more higher fields. But those are, yeah. So we have seen very unique phonon modes. We call this vortex on. This is work Hayden Wen has led, and it's on its way. You might see it soon. And also, we have recently looked at dances for skyrmions, and we see some very unique, beautiful phonon dynamics in skyrmions. And that's only about 2-3 weeks old. So we are still digesting about maybe 50 terabytes of data there. So.
Very nice. And then I guess one more question from me is, so, you have to heat this up to destroy the supercrystal.
Yes.
Right.
Yes.
But also you have these long pulses of light which don't allow you to create the supercrystal. Can I optically heat the system to switch back and forth, or use a longer pulse of light to sort of change the electrons or something in a way that I switch things back? Would be the other question.
Yeah. In fact, these are things that I think Vlad can speak to this, but these are tricks that we have been using, especially single shot circular data. We write in one spot, and then we, in that case, we kind of moved to another spot and kept writing in different spots. But he often uses a sample that's really good. He'll write it, then he'll erase it, and then he'll write again. And there's no reason you cannot erase them with light. So absolutely, if you no, that's one of the ways in which we are thinking we can do optical pump probing, but we can also study dynamics.
Excellent. That's great. It's really interesting stuff. I'm sure lots of additional work will be coming out of it for many years.
I think so. Just, you organize the session, so it's clear that there's a lot of people doing wonderful work here.
Great. So if any other questions come up, we can answer them in the chat from the Slido. Thanks, Venkat, again for your talk.
Thank you.
Our next speaker is